What we're going to do today, and it's going to help us set up for the lab that we're doing tomorrow, or starting. So you guys will do the lab Wednesday, is graphing in motion, or graphing motion in physics. So graphing is just another. It's very important because it's another way to model the motion. And I know in AP Physics we talk about the science practices, and one of them is modeling. Okay, equations, descriptions, graphs, they are ways that we model motion in physics. Okay. Now, these next two bullet points are just a reminder about different things. So recall that the independent variable is plotted on the x-axis, and it is the variable that does not depend on the other one. Okay. It's the one that we just let go, and the other one reacts to those changes in this variable. Sometimes we'll abbreviate it IV. Okay, you'll see that pop up. But again, it's on the x-axis. And for us in motion, the independent variable we're going to work with is time. Okay, time measured in seconds. Although you'll see in one of the examples, it's going to be measured in minutes, but it doesn't matter. As long as your units are consistent for your axes, the units don't necessarily matter. All right. Now, the other variable, and if you remember this from your science classes, especially if you did any kind of graphing in them, right, we have what is called the dependent variable. So this is the one that's plotted on the y-axis, and it's the variable that depends on the other one, right? So once we start our stopwatch, the position is reacting to changes in that time. The speed is reacting to changes in time. The acceleration is changing with depending on the time. Okay. Now, when you title the graph, because you got to make sure you title your graph, so you're going to do dependent versus independent variable. So if you hear a position versus time graph, that is telling you that the position is on the y-axis and the time is on the x-axis. So the way that we plot this, if you want and we call this dv, right, the dependent variable. So you're going to do dv versus iv. Okay, so dependent versus independent variable. Now, when we talk about graphs in motion, we're talking about three types. The first type is what we call a position versus time graph, or a position time graph. You'll hear me call it PT. Okay, and what that does is it puts position on the y and time on the x. Oh, if we go back up to where we talk about this x-axis, so for the most part, physics will graph in the first and fourth quadrants, right? Oh, that eraser's kind of big. So it'll graph in the first and fourth quadrants because time is our variable, right? And that's where quadrant 1 and 4 is where the x-axis is positive, okay? And then now when we get down to, so that's the first graph. We're going to break them down. We're going to do a couple examples. How does it look? How do they break down? How can we interpret these graphs? The second example is a velocity time graph, or VT. So velocity is plotted on the y, and time again is plotted on the x. And we'll break this down again, and then we can go back and forth between the two. And then the last one is an acceleration time graph, or an AT graph. This graph, I'll tell you right now, is probably the easiest graph that we will use. Okay, and this is acceleration on the y, and again, time on the x. Right? And so now we're going to spend some time breaking these graphs down and then doing some examples on how we interpret these graphs. Okay? And the interpretations are different because of those variables and where things are plotted. All right. So our first graph we're going to talk about is our position time graph. So again, position is plotted on the x, or sorry, on the y, and so position is on the y-axis and time is on the x-axis. Now, the shape of the graph tells you if the velocity is constant or if it's changing. So non-accelerated motion, or what we call constant velocity, the shape is going to be they're going to be straight lines. All right, they're not going to be curved at all. All right, so it's going to be linear, and there's going to be two versions or two ways to show that. It's either going to be sloped or it's going to be flat, and we'll talk about that here in 1 second. You can kind of see popping up down at the bottom what that's going to be. Now, if it is accelerated motion, the shape of the graph is going to be a parabola, right, or parabolic, quadratic in its shape, and that comes from the equation that you'll see when we do these constant acceleration kinematics equations. Okay. Now, if the object is at rest, right, it's going to be a horizontal line. Okay, horizontal lines are flat. So anytime you see a flat line on a position versus time graph, it is at rest. Okay, now if the slope of this, if it is a slope line, okay, the slope of that line will be the object's velocity. Okay, and velocity meaning change in position over change in time. So if we go to our math definition of slope, right, we got rise over run, and this is where it comes from. And I like to show this because this is how it breaks down. So mathematically, you got rise over run, or change in y over change in x. But in physics, we name the x and y axis. So for position time, it's change in x over the change in time. But that, if you remember from the other day when we defined velocity, that is just the definition of velocity. Okay, when you see this delta x, delta t over delta t equals velocity, that is what we call a definition. So the left side of this is math. The right side of this is physics. Okay, so but notice that we used a math principle to get to the physics concept. Okay, so we use the definition of slope to now define what the slope of a position versus time graph is. Okay. Now here we have just some general shapes, right? And these are just non-specific generalizations of what these motions look like or what they will look like on graphs. So if we go through the first graph here on the left, this is velocity, and then you have changing velocity. I don't want to highlight those just so you guys can see that what we mean by straight line versus parabola. So scenario A, what does it look like for an object to be at rest? Okay, it's just going to be a horizontal line that doesn't change. So it has a run, but it doesn't rise. So, okay, so your delta t would change, but your delta x will not. A fast positive velocity, well, when you show a fast positive velocity, you want a big slope, okay? And in fact, let me change the color of that, right, so we can get a little variation, right? So fast velocity would be a steep slope, a slow positive velocity, and I'll go back in here a second, right? So remember, positive means it's going to slope upward, right, or increase as you go from left to right. So the closer my line is to the y-axis, the greater the slope. The closer my line is to the x-axis, the slower the slope. Now, for us, it's velocity, right? We name what these are, okay? Now, if we do the fast negative, okay, now the difference would be that it's going to decrease as you go from left to right, as opposed to increasing from left to right. Let me let's do an orange color, right? Because the yellow can get very bright. And now if I want to slow negative, right? Battling the screen control method here, so that would be a slow negative, right? And this would actually push back to the axis there. Okay, so that's what it would look like on a position versus time graph for non-accelerated motion. Now, I know that they're not all straight lines, but understand that those are straight lines. Okay. Now, on a when there's a changing velocity, okay, You got 3 different scenarios. You have a positive velocity, you have negative velocity when it goes from slow to fast, and then you have a negative velocity when it goes from fast to slow. Okay, so because it is changing, it's going to be parabolic in shape. Okay, over on the left side on our non-accelerated motion, the slope remains constant. On our changing velocity side, the slope is going to change, right? So that means the velocity is changing with respect to time as well, which that's our definition of acceleration. So a positive velocity, it's going to be an upward opening parabola. Okay. Now you have the negative velocity from slow to fast. Okay. And what that's going to look like is it's going to be a downward parabola. And here's the reasoning why, right? So we know that velocity is defined as the slope of a position time graph. So if I draw in some tangent lines, right, these define the slopes at those points. Remember, this is where I told you guys that you're doing calculus, but you're not doing calculus. And so what happens is at the top of this, it's going slow. Here in the middle, it's medium. And then as it gets straighter up and down, it's fast. Okay? And so that's what we're talking about from slow to fast. Okay? Now, on the flip side of it, when you do the other way, the negative velocity from fast to slow, it's going to go the other way. Oh, sorry, I want to get a different color in there so we can distinguish these. All right, so it's going to be an upward opening parabola, but we're going to look at the other side of that parabola. But if I do my tangent lines, you can see it's kind of be the reverse, right? So my fast is up here, my medium again is here in the middle, and then I've got my slow down here. Okay, and so that's what we mean by slow to fast or fast to slow. Okay, so that's our position versus time graph look and analysis. Right, and we're going to do an example where you guys can see how this is broken down. Okay. Let me